Today I would like to walk you through our journey of building an efficient AI inference platform on a geographically distributed network. Briefly about myself. I'm a systems engineer at Cloudflare, and my career path has started around 15 years ago as a backend engineer. And after a number of turning points, I ended up working on infrastructure, optimizing for resilience and scaling. After joining Cloudflare in 2018, I've been working on different parts of the stack, starting as a SRE and platform teams, and then gradually moving to product, primarily overseeing architecture and infrastructure. So it's a lot to uncover in one talk. So I'm planning to give a high overview of situation we had at the launch of Inference platform, the challenges we faced during scaling up on top of our existing distributed network, and the ways to overcome them. I actually want to ask a couple of questions. How many of you heard about Cloudflare? Can you raise your hands? It's quite a lot, yeah. And the second one is, how many of you are a customer? It's a bit smaller. All good. Yeah. For those who didn't hear about Cloudflare, so Cloudflare is a cloud provider originally focusing on CDN, DNS, and network and security. And surprisingly, there are so many people still today that have strong association with these services. It has become so much more since the launch of Workers, our developers platform in 2017. Started to turning in a full-fledged cloud provider, allowing developers to build on top of serverless databases, object storage, queues, media, AI containers, so much more. In fact, the pace of launching new products every year on birthday weeks still happens to surprise me over the years I've been working for Cloudflare. A quick remark. These days, AI inference on the edge can confuse people with running models on user devices, which is not the case for us. So we have a geographically distributed network for many data centers, more than in 300 cities in the world. One of the biggest customer-facing interconnected networks, residing with up to 50 milliseconds from 95% of internet-connected population. So entire network is built on a bare metals, and we managed it internally. And so I will call this network the edge going forward, because it's really hard to say it, and I don't want to break my tongue. At Cloudflare, we've been using ML models for a long time to drive our bot detection product. So these models are small and can be run on a CPU and on any node. So since bot detection system need to run on every request, it's highly latency sensitive. Another example of running inference was introduced a few years back when I was on an images team. We were working on a face cropping project. And so we had the need to run a face detection in order to crop the image. And it has to run on the edge as well, close to where we serve and resize images. So back then, there were no GPUs in our edge fleet yet. So we had to run this model on CPU. So running this model on CPU was possible, albeit slow. So we had to improvise. In 2023, around the same time, on the birthday week, Cloudflare launches a Workers AI platform in beta, allowing to run inference on a small set of L4 GPUs, and with the 6 different categories of open source models. A year after the launch, I joined the Workers AI team to help make inference at our scale more efficient. So fast forward to today, we are running almost 100 different models from the catalog on heterogeneous hardware installed in over 200 cities across the world. So let's imagine the situation. You receive an alert at night, and the model latency going high, and you look at the dashboards, and some of the GPUs in Frankfurt are hot. And you look at London, and their utilization is measly 25%. So it's not a one-off situation. It's everyday reality running inference on the edge. So there are two big differences in these approaches. If you run inference on a centralized cloud, it's probably much easier to just put an autoscaler and scale up the pods like candies, and that's it. But on the edge, it's very different. We have to fight geography, laws of physics, and economics, and all at the same time. So Cloudflare network is our power and a challenge at the same time. Having big network is a huge advantage. It does help to absorb massive DOS attacks, and globally distributed data centers allow it to be as close as possible to the end user. It serves well in a serverless world where most of the traffic is homogeneous, small enough to get processed at the local data center, and it's mostly IO bound. But when it comes to inference, it's a different nature. Inference can take time, which holds a GPU. Cold starts are expensive. Virtualization adds an overhead. So GPU utilization is held back by laws of physics. The farther away the placements, the more everyone is paying the price. Underutilized platform and a bad user experience. So it's much easier to run payloads on a high-density GPU sites, but it's not how our network is built. So we have to face this challenge and to solve it and make it our advantage. Our AI platform is not just a container platform. It's a model catalog with the different requirements. So running AI inference on a distributed network presents a unique set of challenges. There are two different categories requirements related to model placement and a catalog. So if you look at the placement, we have to first treat the security, and we need to run third-party code. So then we have different hardware profiles. So GPUs are not installed everywhere, different drivers and different kernel versions. Another thing to think about is the collocation with other services we have to run on the edge. And we have a resource constraint. So when we talk about model catalog, it's ever-growing model catalog is different throughput and latency requirements, and the varied traffic demands over the days and weeks competing for finite GPU resources. A critical and yet often elusive objective in this domain is achieving high GPU utilization, which directly impact both the operational cost and service quality. Underutilized models are a significant financial strain when over-utilization can degrade user experience. It's a balancing act and stakes are high. As you already know from previous talks today, GPUs are not cattle, they're very expensive. So with growing demand in inference, we have to increase footprint and install more and more GPUs across our network. And in order to be efficient, we need to drive down the costs. So the question I want to think you about is, how do we achieve this high utilization without sacrificing latency and reliability? In order to achieve this goal, we need to approach it from multiple angles. The system architecture underpins the scalability and efficiency on the edge inference platform. And it's structured around several essential components: container platform, edge coordinator, and a scheduler. So let's zoom in and walk through the components from the bottom up in the system architecture. As I mentioned, Workers AI platform catalog counts dozens of models falling under different categories, each with unique requirements and dependencies. Those categories require a set of different libraries and frameworks to run, which ranges from Triton to Ray to VLLM and beyond. So running untrusted code on the edge in a shared environment raises security concern for us. And our first priority is to put isolation mechanism. So containerization might seem like an obvious solution, but it brings its own set of challenges. It's because not all container runtimes support GPU pass-through. Models have different GPU memory needs, and GPU slicing is not trivial with our runtime. So model libraries with all dependencies are adapt fast as well. So let's dive into how we solve each one of these. And first, model placement are based on GPU profiles and requested resources. So container platform knows which Cloudflare location have available blocks of GPUs and then schedule a workload on a specific model. So this allows us to prioritize placement of AI models that use a large amount of GPU memory and then move smaller models to other machines. There is an option to set affinity placing option to cluster model instances together. This allows us to group some models closer to each other, improving overall throughput. The second, container runtimes and GPU support. Thankfully, from the day one, we've built our container platform with runtime to be a runtime agnostic. So using a runtime agnostic orchestrator, we are able to support Gvisor, Firecracker, and Kimu. We're also evaluating adding support for another one, the cloud hypervisor. But lastly, Docker images alone can be a bottleneck because it is huge on a startup time. Having an access to code in open source models give us a huge opportunity for optimizations. One of the popular libraries to run LLMs is VLLM. So it's a mature and developed project and has a lot of support in the community. It's open source, written in Python with a great, so it's very great for prototyping, and it's very great to run on dedicated hardware. But alas, it's not best fit for us to run on the edge. For example, VLLM does not support hosting multiple models on the same GPU without using a multi-instance GPUs. More importantly, running third-party Python libraries alongside the rest of the services forces us to run VLMs with Gvisor in a sandboxed environment, which leads to increased already long cold starts and consumes precious CPU cores shared across the system. So to tackle this challenge, we designed a bespoke inference engine optimized for our shared resource infrastructure. I will not go into the details of this implementation, but here's a summary of the key feature of our engine. So Inference just-in-time compiles its kernels for a specific model it's running, optimizes for models parameters such as hidden state size, dictionary size, and GPU it's running on. So for some operations, such as large matrix multiplication, Inference will utilize the high-performance cuBLAS library if it thinks it would be faster. Inference also makes use of very fine-grained CUDA graphs, essentially creating a dedicated CUDA graph for every possible batch size on demand. Conceptually, a CUDA graph is another form of just-in-time compilation. The CUDA driver replaces a series of kernel launches with a single construct, the graph, that has a significantly lower amortizing kernel launch cost. Thus, kernel executes back-to-back faster when launching a single graph as opposed to individual launches. At this stage, we were able to achieve 7% boost on throughput compared to VLLM running in Gvisor on the idle CPU cores, while in CPU-constrained environment, which is a normal case for us, it's up to 50% improvement, which is a great deal. So with growing demand on AI products, developers are creating and tuning a variety of models. And as you might guess, not all of these models used equally. But there is a tail of models that receive either infrequent requests or traffic patterns are so unpredictable that leaving models to run idle, wasting scarce GPU resources. To solve this challenge, we've built an Omni platform. Typically, deploying a model requires its own dedicated container. But we want to collocate more models on a single container to conserve memory and GPU capacity. In order to do so, we needed fine-grained controls over CPU memory. So Omni can be deployed either in a container running multiple models or bare metal running in Fire, as I mentioned earlier. So in both cases, process isolation and Python virtual environments allow us to isolate model with different dependencies by creating namespace and limited by cgroups. Unfortunately, Python doesn't take into account cgroup memory limits for memory allocations, which can lead to out-of-memory errors. So many AI Python libraries rely on ps-util for pre-allocating CPU memory. And since in Omni, each model has its own configurable memory limits, we need to ps-util to reflect this current usage and limits for a given model, not for entire system. So the main purpose of Omni is also to allocate multiple models on a single GPU, which doesn't work well in our general container platform. Instead, Omni is responsible to place models next to each other and overcommit GPU memory, swapping between models when needed. Overcommitting memory means allocating more memory than is physically available on the device. Right now, Omni is configured to run dozens of models and allocating about 400% of GPU memory on a single GPU, saving up 4 GPUs Omni an instance. Omni does this by injecting CUDA stub library that intercepts CUDA memory allocations and forces to be performed in a unified memory mode, meaning CPU and GPU share the same address space. Another benefit of Omni, it allows us to control how much memory is actually exposed to any given model to prevent the greedy model from overusing the GPU allocated to it. So we do this by overriding the CUDA runtime and drivers API. Instead of exposing the entire GPU memory, we only expose a subset of memory to each model. Every edge site has what we call an edge coordinator. So specifically, coordinator controls the following things. It handles incoming sync request and pull queues from async workload. So it understands the model protocol. It can talk to HTTP and gRPC and whatever. It prepares and distributes requests to model instances and collect metrics and logs. Every model has its own concurrency limits. So some requests can take longer than others. With a naive round-robin approach, there will be a long tail of requests with elevated latencies being stuck on waiting for free resources. Imagine an example. You probably remember yourself being in a supermarket, joining the queue at the till, and you're noticing that some other queues are moving faster. That's the similar example here. And in order to prevent the long tail of requests, we want to eliminate such behavior, and we introduce the permit manager. This is essentially a single queue ticketing system designed to distribute incoming requests across visible instances to an edge coordinator. So using permit-based balancing algorithms, every request tries to acquire a permit for a model. Once acquired, total capacity for a model reduced. When there is 0 available permits, edge coordinator will try another one in another data center. So what's more important, permit states are per model and stored in memory. So it's very fast to check, acquire, and release without an extra network calls. It's far from perfect, but it's already something. So response can be big, client can be slow. We don't want to hold release longer than necessary. So what if we can notify coordinator inference has finished? So when response is ready on a model server, we can communicate an early release back to the edge coordinator and send the response to client with its own rate without hogging the pricey GPU. And as you can see on step 5, that's what we actually do. It is especially valuable for diffusion models where response is often large and the client can be slow. Do you know what else is involved in diffusion models? It's CPU. So when diffusion model finishes inference, we need to make our CPUs to make some work and encode an image on video. So diffusion model is usually a denoising mechanism to generate the images and video. And unfortunately, modern GPUs like H100, they don't have hardware encoding. So we have to offload this encoding to CPUs. But we don't want to hold permit for extra 200 or 300 milliseconds. This is very beneficial. So some might say, Alex, this is still suboptimal. So every edge coordinator can have a local queue configured for every model, allowing to queue a fraction of the request from total permit capacity in the data center. We're waiting in a queue for a free permit might be faster than going to the next data center. But how can we know this? So diffusion model are a good candidate for this again. So it's possible to predict the time it takes to run inference based on an input data, like prompts, steps, and dimensions. And in fact, many inference servers like Automatic and Confi.ui are actually able to pre-compute ETA based on these parameters. So what if all of the above load balancing strategies, we need to add another dimension? When the model generates text or tokens, it looks at all the previous tokens to predict the next one. So normally, it would repeat the same calculations for every new token, which can slow things down. KV caching solves this compute overlap by remembering these calculations from previous steps, and this can be achieved by storing the intermediate state of attention layers during the inference. For chat models, when a context is passed back and forth, it's even more beneficial. So we can save on a repetitive computation and improve performance. So in order to do this, we can refer to a sticky routing. So this is the concept in the load balancing, where a request is sent to the same edge node that handled the previous request. Obviously, this solution has trade-offs. So the same node can be busy making the waiting time in a queue for potentially longer than savings applied for the KV cache. If request routed to a busy node, we can actually check the chat length, and the longer the length, the longer we can afford to wait in the queue and optimize for routing. So in a resource-constrained environment, there is a need to balance load between users. Some might send a spike of requests modern system can handle or attempt an abuse. It can still be legitimate traffic sent. It can still be legitimate traffic sent in uncontrolled manner. So rate limiting is one of the most common solutions for this problem, and it can prevent from abuses, but it's not enough. So it's a coarse-grained mechanism and a very imprecise, especially when running at the edge. So let's look at the example. We have two customers, A and B, and initially they run a very steady flow of requests. And then customer A decides to send 100 requests per second. We can see that maximum system capacity is at 50. So default behavior for every resource constraint shared environment is a proportionally serve request and drop the rest. And as you can see on the diagram, when the customer A starts sending much more traffic, shares have drastically changed in their favor. Customer A is able to get 42 successful requests jumping from 20, while customer B is seeing a drop from 20 to 8. So one customer can negatively affect the others. So this is not fair. A better way of sharing resources is to use fair queues. So it uses one queue per user, serves them in rotation, and such that each user can get a fair share of resources. With this approach, each user can get fair share of resources, and there is no need to artificially limit them when they're only user of the model. So there are still downsides in a few scenarios when a multiple of users are misbehaving. But the bonus point of having a fair queue, it's possible to extend them with a weighted fair queue, allowing to balance customer share. All models are different in a way. Each require a different amount of resources. Some need a few GPU of memory and can run on L4s, and others need entire H100s. And some can only run on a multi-way setup requiring multiple GPUs linked together. In addition to these dimensions, every model can have different throughput and latency requirements. To solve this puzzle, we introduce scheduler. So this is a main decision taker, so to say. It lets every part of the system, it tells every part of the system what to do. The scheduler acts as our automatic network operator center, coordinating resource allocation across the globe, traffic routing optimizations, utilization prediction and scaling decisions, and also model version management. So it needs to make decisions across multiple dimensions: geography, resource, and time. So one of the key features of a scheduler is the ability to request as less resources as possible to be in the utilization targets. So imagine model A and model B are running on one GPU only, and the initial states are set to be the same. Each model has minimum one instance required. A few moments later, model B is getting traction and start receiving more traffic. So to prevent the system from being saturated, we need an autoscaling. So in order to do that, we look at the utilization metrics collected from all instances running this model. So in order to collect these metrics, we use multiple of data sources like ClickHouse and Prometheus. So although hardware utilization metrics exposed by GPUs are very valuable to have, they don't entirely represent overall utilization, including all components of the system. So to understand utilization, for a model, we are interested roughly in a few things over the last 20 minutes. So how much wall time spent on GPU, how many permits used by a model, queuing time on every edge coordinator, and amount of out-of-capacity requests. So these metrics give us good indicators in overall utilization, model usage, waiting time, and rejections. So looking at these indicators, scheduler asks container platform to scale up or down a model. But the issue with this approach, it's reactive and very inert. First of all, we look at the utilization in the past 20 minutes, which can easily change in a minute. So second, it takes time for a model to scale up. And third, traffic can be spiky, influx of new requests can be rejected with out-of-capacity errors, and which can lead to customer dissatisfaction. So auxiliary technique is to use forecast metrics. The same approach as with utilization, but look at the multiple time windows back to predict the future. This gives us a rough estimation of what's ahead. With having hundreds of data centers around the globe, it's not always possible to place a model closer to a customer. Running every model in every data center isn't financially viable, and serving all customers from one location isn't feasible either. So the solution is to optimize routing, finding the shortest path between the model and the customer. So the other but not less important key component of a scheduler is a routing guide. So it calculates the latency probes between each and every data center and distributes them periodically across our network. So an edge coordinators in data center read this latency map, intersect with model placements to find the best path to reach an instance. As I mentioned earlier, every model has its own requirements for latency and throughput, so there are multiple routing algorithms to choose from depending on the goal. So we've developed a framework to test all of the routing algorithms we've developed, we come up with all the permutations. We've tested on 4 different models, under various conditions. To our surprise, the random choice on a nearby data center turned out to be the best default option. The observation showed the random choice of nearby data centers will have better chances of finding a free permit rather than following almost the same path for every request. So what lesson we learned through this journey is the first one is running inference on the geographically distributed network is hard. When there are so many moving parts in the system, distributed tracing is a must. I haven't mentioned it throughout the presentation, but it is necessary. It's helped us to find many nuances early on. So gvisor adds a lot of overhead, and we need to look into cloud hypervisor to run big models. So Python is a great tool to develop at speed and run experience, but it lacks performance. So investing in Infi allowed to optimize LLMs and run them natively. So running a long tail of catalog models is not ideal use of resources, but we value our customers' requests, so we're able to oversubscribe GPUs multiple times, which helps reduce the CapEx without impacting performance. Driving down error margins on predictions is one of the goals in these directions. It's hard to make it perfect, but it works better with diversity of users. The more customers requesting a model, the better amortization we can get. So the better prediction we get, the better utilization achieved. So address spiky traffic, providing async workloads, and it can smooth out demand. So this is the ideal choice. Being closer to our clients is our motto. It's in our DNA. But we don't have to run a model across the globe if the clients are only in Europe. So clustering model instances together reduce unnecessary hops in between locations. It simplifies routing and reduces latency, improves throughput, and enhances utilization. Traffic patterns are dynamic. Adaptive routing strategies along with permit management and local queues are the way to fight chaos. Let's have a history lesson. After World War II, oil was very cheap. In fact, it was so cheap for many years, there was no incentives to look into development of renewable energy and efficient engines. This 1966 Pontiac is a very beautiful car, some can argue, but it's very inefficient by modern standards. Then in the 1970s, the oil crisis came and triggered an overhaul in many industries that we can enjoy today. All has to happen because of the main resource constraint, money. And we all know how many engineering work has to be done to achieve all of these improvements. So we are facing a similar situation today. Demand continues to rise, models keep growing in size and diversity, and the longer the chain of thought, the larger context windows. Although order backlogs are easing, hardware remain costly and keep being a major constraint. So we have to use it as our advantage. And I would like to finish with this quote, where nothing resists us, nothing sharpens us. Without the hunger, there is no invention. Without limits, no discovery. Abundance lulls us into complacency, dissolves discipline. Constraints are the forge where the greatness is made. Remove the forge, and all that remains is decay masked as comfort. Thank you.